What is a gas-insulated substation? A gas-insulated substation GIS is a high-voltage substation in which the major conducting structures are contained within a sealed environment with a dielectric gas known as SF6, or sulfur hexafluoride gas as the insulating medium. In comparison, a conventional AIS or air-insulated substation, atmospheric air is the dielectric gas medium, as these types of substations are almost always located at outdoor locations. Origin of GIS technology. GIS technology originally began in Japan in the 60s, where there was a critical need to develop substations with a greatly reduced footprint. GIS was slowly adopted by various other countries over the following years. After about 5 years of evaluation and testing, GIS system construction increased to about 20% of new substations in countries with severe space limitations. For countries with space readily available, a higher cost of GIS relative to AIS has limited its adoption to special needs cases. In the US, only about 2 to 5% of new substations are constructed as GIS. Clearances for GIS, roughly a tenth of that for AIS. With GIS technology, the clearance needed for phase-to-phase or phase-to-ground for all equipment is much less than that of an AIS or air-insulated substation. The total space required for a GIS is roughly a tenth of that needed for a conventional AIS facility. While the conventional AIS requires several feet of air insulation to isolate a conductor, SF6 gas insulation only needs inches, allowing a GIS facility to fit into areas far smaller than that of an AIS facility. A GIS is mainly constructed where real estate space is expensive or scarce. Environmentally protected system GIS technology is a good choice to use in Arctic or desert locations, as it can be enclosed in a building which is environmentally protected from extreme conditions. In addition to protecting the system components from extreme heat and cold, GIS technology encloses the electrical components within a Faraday cage which shields the system from potential lightning strikes. Gas-tight modular design. Each compartment housing the live sections of the GIS system is gas-tight, with respect to one another. This ensures that the gas is not allowed to pass to an adjacent module, as well as ensures that gas monitoring is independent. O-rings are installed at the equipment and enclosure flanges to ensure the gas-tight integrity of the modules. Gas monitoring system. This includes an integrated alarm system, as well as automated tripping and lockout features in case of low-pressure conditions due to leakage. This is critical, as when the pressure of the dielectric gases drop, so does the insulating capability of the SF6 gas. High-voltage installations. Gas-insulated technology becomes more desirable as the voltage requirements increase. As an example, the footprint of a 765 kV conventional substation is considerably large. A station footprint of this sized station would be significantly less were it to employ GIS. Expansion of existing AIS. Mixed technology switchgear. One approach to the expansion of existing AIS is mixed technology switchgear or hybrid GIS. This approach is especially suitable for the expansion of an existing substation, without requiring large areas of additional real estate, which is often unavailable. This design uses GIS breakers, switches, and voltage current transformers with interconnections between the breaker positions and connections to other equipment using air-insulated conductors. Indoor installations. The construction of an indoor air-insulated substation would be highly impractical and difficult to operate safely. However, a gas-insulated substation can easily go inside an industrial building. It can be incorporated into the electrical infrastructure of an industrial facility, allowing for on-site stepping down of voltage. The GIS system's foundation. GIS systems are usually installed on a monolithic concrete pad or directly on the floor of a housing facility. The system is attached by bolting or welding the GIS support frames to embedded steel plates of beams, or by the use of chemical drill anchors. Expansion joints. Expansion drill anchors. These are not recommended, as the dynamic loading from circuit breaker operations may loosen the expansion anchors over time. Bus expansion joints. This type of expansion joint may be recommended in the large GIS installations. The expansion joints are installed between the various sections of the GIS to adjust to the fit-up in the field. They can also be installed to address thermal expansion of the GIS system. Disadvantages of GIS systems. System cost is higher compared to that of a conventional AIS. Delivery of SF6 gas to the site can be problematic. GIS substations are indoor type, requiring a separate building. System cleaning maintenance are critical to reduce conductive particle contamination. Particle or moisture contamination inside the compartment causes flashovers. Outages can be extremely long, and the damage to the system will normally be severe following a fault condition at a GIS substation. Access to live parts for maintenance is more problematic, and harder to diagnose without gas reclamation and disassembly of the modules. Disadvantages of the conventional AIS system: equipment deteriorates when exposed to ambient atmospheric conditions. Equipment becomes contaminated when exposed to pollutants such as airborne particulate matter. Requires a lot of real estate, which can be expensive to acquire in dense urban areas, may require the use of eminent domain to secure the necessary parcels. Less stable, with reduced safety of operation compared to GIS, in seismic regions. Requires regular maintenance. Requires special consideration in regions with altitudes higher than 3,000 feet mean sea level, due to the lesser density of the dielectric gas atmospheric air. The poor dielectric properties of air, as well as secondary factors such as humidity, pollutants, salt, and moisture means that more space is needed. SF6 gas. A gas-insulated substation GIS uses a superior dielectric gas, sulfur hexafluoride SF6, at a moderate pressure for phase-to-phase and phase-to-ground insulation. The high-voltage conductors, circuit breaker interrupters, switches, current transformers, and voltage transformers are totally encapsulated within the grounded metal enclosures surrounded by pressurized SF6 gas. GIS protects components from exposure to the elements in a GIS. The active components of the system are protected from deterioration due to exposure to atmospheric air, moisture, particulate contamination, etc. This results in a system which is more reliable, requires less maintenance, and will have a longer service life in excess of 40 years than its conventional AIS counter. Popular physical arrangement for the GIS. For any one-line diagram there can be several possible physical arrangements. When deciding upon the physical arrangement, the shape of the site for the GIS and the nature of connecting lines and cables should be considerations. Double bus bar configuration. Most GIS designs were initially developed for a double bus, single break arrangement. This popular approach has good reliability, and is simple to operate. Additionally, it allows for easy protective relaying, excellent economy, and provides a small footprint. What is SF6 or sulfur hexafluoride gas? Sulfur hexafluoride is a non-toxic, inert and non-flammable gas consisting of a sulfur atom surrounded by and tightly bonded to 6 fluorine atoms. Sulfur hexafluoride SF6 is the most common insulation gas in high-voltage technology because of the electron attachment electron affinity. SF6 is around 5 times the density of atmospheric air at mean sea level, and has no color, odor, or taste. SF6 is almost purely water insoluble, and as with all other gases, its solubility decreases as the temperature of the water increases. SF6 gas pressure. SF6 gas is enclosed in GIS systems at pressures between 400 to 600 kilopascals absolute. This pressure range is ideal to prevent the gas from condensing into a liquid at the lowest potential temperatures which the equipment may be subjected to. SF6 is a gas in which the speed of sound propagation is about 3 times less than in air, at atmospheric pressure. The sound of the interruption of the arc will thus be quieter in SF6 than in air. Dielectric strength. SF6 gas versus air. SF6 has a 3 times higher dielectric strength at 0.1 MPa, 1 atm or atmospheric conditions compared to air. When the pressure within the GIS enclosure increases, so does the dielectric strength of the SF6 gas, due to the increase in density. At pressures such as those within a GIS enclosure, the dielectric strength of the SF6 gas can become much higher than that of atmospheric air. Arc interrupting ability of SF6 gas. SF6 tends to be roughly 100 times more effective for interrupting arcs than air. SF6 has become the standard for interrupting mediums, used in high-voltage circuit breakers applications, replacing older insulating mediums, composed of oil and air. Recycling SF6. When severe situations of gas contamination occur, the SF6 manufacturers will take back the contaminated SF6, and reprocess it, in effect turning it back into a new SF6 product. Permanently retiring the gas. Though not yet a common situation, an end-of-life scenario for the eventual retiring of SF6 gas product, is the incineration of the SF6 along with materials that will enable it to become part of environmentally acceptable gypsum. Types of equipment modules. GIS systems are assembled from standard equipment modules. Types of modules include circuit breakers, current transformers, voltage transformers, disconnect and ground switches, interconnecting bus, surge arrestors, connections to the rest of the electric power system. Single-phase and three-phase enclosures. Systems up to around 170 kV. All three phases are often combined into one enclosure. Systems above 170 kV. The size of the three-phase enclosure becomes too large to be practical, so a single-phase enclosure design is used instead. No established performance differences exist between the three-phase enclosure and the single-phase enclosure GIS, with some manufacturers using single-phase enclosures for all levels of voltage. Joining and sealing enclosure modules. GIS enclosure modules are joined together using bolted flanges which have an O-ring sealing system for the enclosure. The conductors have a sliding plug-in contact for connecting the conductor sections. Rupture discs. Rupture discs are commonly used as a safety measure in pressure vessels, although the pressure rises caused by internal fault arcs within a GIS compartment of the usual size is predictable and gradual enough that the protective system will interrupt the fault before a dangerous pressure is reached. Periodic inspections of internal components not required. There is typically no need for periodic inspections or maintenance of GIS internal components. Dry inert gas environment. The interior of the enclosure is dry, with an inert gas environment that is not subject to aging. UV exposure. Additionally, there is no exposure of any of the internal materials to sunlight and the damaging effects of UV radiation. Module seal deterioration. The O-ring seals in the modules are normally found to be in exceptional condition, because there is usually a double seal system, with the outer seal protecting the inner seal. Circuit breakers. Both AIS and GIS use basically the same type of dead tank SF6 puffer circuit breaker. However, with GIS systems, instead of SF6 air bushings mounted on the circuit breaker enclosure, the GIS circuit breaker is directly connected to the adjacent GIS module. Current transformers. For GIS applications, current transformers are devices which are installed in substations for the purpose of transforming the high current from the conductor into standardized, equivalent values, which are then used for purposes of metering, measuring, and protection. Installation location. Current transformers installed in a GIS system are of the inductive ring type, and can be installed either inside or outside the GIS enclosure. Metering and protection are performed on the secondary winding side of the transformer. The GIS conductor is the single-turn primary for the current transformer unit. Considerations for current transformers. For CTs installed on the inside of the enclosure, they must be shielded from the electric field produced by the high voltage conductor, otherwise high transient voltages can appear on the secondary winding through capacitive coupling. For CTs mounted on the outside of the enclosure itself must have an insulating joint, and enclosure currents shunted around the CT. Both of these types of GIS construction are widely digital output signals from CT's analog relays. Advanced types of CTs have been developed to save space and reduce the cost of GIS by removing the magnetic core or Rogowski coil. The output signals of these types of CT units are at a low level, allowing for the immediate conversion by an enclosure-mounted device into a digital signal. Once the signal is digital, it can be transmitted over long distances via wire or fiber optic cabling to the control or protective relays. One issue though is, many protective relays being used by utilities do not presently accept a digital input even though the relay may be converting the conventional analog signal to digital, prior to processing. Voltage transformers. VTs used in GIS applications are the inductive type with an iron core. The VT is usually a sealed unit with a gas barrier insulator. Installation. Option 1. The VT is easily removable so the GIS can be high voltage tested without damaging the unit. Installation. Option 2. The VT is provided with a disconnect switch or removable conductor link. Primary winding is supported on an insulating plastic film immersed in SF6. To prevent capacitive coupling of transient voltages, the VT should possess an electric field shield between the primary and secondary windings. Disconnect switches. Components of a disconnect switch include a moving contact that opens or closes a gap between stationary contacts, when activated by an insulating operating rod that is moved by a sealed shaft which runs through the enclosure wall. Stationary contacts. These have shields that provide the appropriate electric field distribution to avoid too high a surface electrical stress. Contact operating velocity. The velocity of the moving contacts in a disconnect switch is relatively low in comparison to that of a circuit breaker's moving contacts. The disconnect switch is only able to interrupt low levels of capacitive or small inductive currents. Ground switches have a moving contact that opens or closes a gap between the high voltage conductor and the enclosure. Sliding contacts. These electric field shielded contacts are incorporated at the enclosure and the conductor. Maintenance ground switch. This type is operated either manually or by motor drive to close or open in several seconds. Fully closed, it can carry the rated short circuit current for the specified time period 1 or 3 seconds without damage. Testing of gas-insulated switchgear GIS with SF6 gas involves several important steps to ensure the equipment's reliability and safety. Mechanical tests, gas leakage and gas quality. All gas compartments are filled with SF6 gas or a required gas mixture to the manufacturer's rated filling pressure and tested for gas leaks. This includes testing all enclosure flanges, welds, gas monitoring devices, gas valves, and interconnecting gas piping. Moisture content. The moisture content of the gas is measured prior to energization to ensure it does not exceed the manufacturer's specified limits. Gas purity. The purity of the SF6 gas is verified to meet the manufacturer's requirements. Gas density. The density of the gas is measured and verified to be in accordance with the manufacturer's nominal rated filling requirements. Electrical tests, contact resistance. Measurements of the main current carrying circuits are performed on each bus connecting joint, circuit breaker, disconnect switch, grounding switch, bushing, and power cable connection to ensure resistance values are within specified requirements. Low-frequency AC voltage withstand test. The gaseous and solid insulation of the GIS is subjected to a low-frequency conditioning voltage application at specified levels and durations. Partial discharge PD measurements, ultra-high frequency UHF methods, used to detect PD activity within the GIS. Acoustic methods, detects PD by capturing sound waves generated by discharges. Chemical techniques, monitors PD by analyzing the chemical byproducts of discharges. These tests help ensure that the GIS operates safely and reliably under various conditions. Considerations for selecting AIS or GIS technology start to come along in the asset planning stage. Once power system or transmission planning has decided the requirement for a retrofit or greenfield substation, different elements have already been assessed, such as system stability, reliability, and load flow needs. The possibility to choose AIS or GIS technology at this point may be early, but data made during the planning process may already start guiding the user and investor to a suggested solution. Environment considerations, locations with harsh conditions, such as poor soil, great air pollution, high seismic, or storm surge, are possible considerations created by the natural environment of a potential substation location. Nevertheless, other qualitative elements associated to the environment, such as aesthetics to the local district, licensing issues, and/or urban area effects can play into the optimal substation solution. Economic considerations. Economic assessment of an asset depends on the importance a substation user gives to each determining element. Also, dominating elements can change with each substation usage. Hence, in order to comprehend the complete investment of a substation project, many end users are turning to life cycle cost assessment. This assessment provides the user with data on how much a substation will cost over the lifetime of the devices. When AIS is cross-compared to GIS technology with respect to the upfront investment price, most of the time AIS technology will result in the least expensive answer. Nevertheless, factoring in land purchase, licensing, site preparation, and O&M prices gives a more holistic approach and may alter the optimal substation solution. Innovation or non-traditional designs, such as GIS technology, can provide more reliability for the same budget under the right considerations. That is why it is vital for traditional engineering techniques, such as N-1 assessment, to be highlighted with a reliability-based lifecycle cost planning approach. Conclusion: when determining between AIS or GIS technology, some elements alone, for example aesthetics, may be an overcoming impact on a user's conclusion. Nevertheless, most of the time the best conclusion asks for assessing many elements and soliciting input data from many sections within an investor's organization. It is also critical to note that the optimal substation arrangement may not be solely AIS or GIS. Sometimes a mix of the two, i.e., hybrid or mixed technology, might be the best arrangement. Typically, most of the factors will prefer GIS technology, but it is the value or importance given to the considerations that decides if the return on investment is justifiable to choose GIS over AIS technology. Consideration that can be measured should be assigned importance weights based on the user's needs.